let's talk about isomers in inorganic complexes. So, as an example here, I actually have two isomers, and you'll see that one of them's purple and the other one's green. And these have the same chemical formula, and it is tetraamine dichloro cobalt 3 chloride. And the purple one is the cis configuration, and the green one is the trans configuration. So let's draw out what those configurations look like and discuss a few other isomers that we can have when we're looking at inorganic complexes. So let's start off by drawing this cis configuration, or the purple compound. So we have cobalt, and then we have our octahedral geometry, and these are coming out of the page. And these are really going into the page. I should have dashed that line too. And then these two positions are contained within the page. So cis means same side. And so these need to be on the same side of the metal. Now, that could be these two positions, or those two, or these two, just not on opposite sides. So if I put the chlorine here, I could not put it there, for example. That would be the trans configuration. So let's just draw one of the options for drawing the cis configuration. So we'll put Cl's here and there, and then the rest of the locations are going to have ammonias. Now, you might wonder why I write this H3N, and that's simply because the nitrogen is doing the bonding to the cobalt. And over on this side, it's just the way to write it. Now, this is the cis configuration. So in naming this, we would just say cis tetraamine dichloro cobalt. I'm going to run out of space over here, so I'm just going to write it down here. Because this whole thing actually has chloride on the outside of it. So this is the cis configuration, same side of the structure. And we could have actually put the chlorines here, we could have put them there, anywhere that they're not directly opposite. So let's draw the trans configuration. And I think possibly in this case I'll avoid writing out the name again, because the only thing that will change is just this cis will change to trans. So I'm just going to write the trans right here, and then you'll know that it's still tetraamine dichloro cobalt 3 chloride. So we have cobalt, just like this. Now, in this case, we need to put the chlorides on opposite sides of the metal. Still have a chloride out there. So it doesn't really matter where we put the first chloride, it just matters where we put the second one. So if we put the first one here, say just like we did over here, we'll have to put the second one right here on the exact opposite side of the metal. If I put it in any other location, it would be the cis configuration, the cis drawing. put it here, 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 or there, those are all cis configurations. Only exactly opposite is it the trans. And then we fill out the rest with our ammonias. Now, cis and trans isomers are not the only kind of isomers that we can have in an inorganic complex. We can also have facial and meridian isomers. So, what would that look like? Well, we'll have to change the complex because tetraamine dichlorocobalt 3 chloride cannot have facial and meridian isomers. We actually need 3 ligands that are the same, and I'll just keep the other 3 the same as well. So we'll have, say, triamine trichlorocobalt 3 chloride, and we'll draw that. And there are 2 isomers for this complex. So, again, we'll draw our cobalt complex. And in this case, we have 3 chlorides and 3 amines to place around the complex. So, let's draw the facial isomer first, because it's kind of similar to the cis isomer, in that we have all of them on one face of the octahedron. Almost said tetrahedron there. So, chloride there, there, and there. And these all form a triangle on one face of the octahedron. So this is the facial isomer, which is sometimes abbreviated FAC, or FAC isomer. And then we have ammonias over here in the other positions. So, to name this complex, we would have facial isomer, and then triamine, trichloro, and then just cobalt 3. I think I can fit it. And since we have 3 negatively charged ligands, we don't have any other ligands in the outer sphere of this compound. So this is the facial isomer, where all of one of the ligands are on one face. We can kind of draw a triangle here that's one face. And then we have the meridian isomer, which is abbreviated MER. So let's draw that one and see if we can see the difference. Okay, so for the meridian isomer, we can keep the chloride here, and we can keep one here, but we can't put it there because that would be the facial isomer, just like we had here, right? And we can't put it there because that's just a face, like that's the facet facing us. We could put the other chloride either here or there. So I'm going to actually just stick it right here. And now these are all in one meridian, or the way I've drawn it, these are all in this plane, one straight line in each other. And then we would put the ammonias in the other position. And these are all in one line. And so let me draw another view of this. Maybe a little bit more edge on. So let's see here. I'm going to draw this very skewed. And then that's going to be like way back there. And then my CLs are like this. So in this case, I've drawn the CLs as the plane of the paper, and then the ammonias are all like this one's coming out of the page and that one's going into the page, right? So these are all in one flat meridian, right? One plane. And these are all contained in the same plane. Now, if I drew the same thing over here, it would look like this. So these are all on one face. So there's like this triangle here. Actually, I could probably draw the triangle a little better over, at least over there. But this is all on one face of the octahedron. Maybe it's better to just muddy up this picture right over here by drawing the triangle like this. Right? See how they're all in the same triangle? I can't do that over here. Right? If I try to draw the triangle on this one face, I will have one of the nitrogens or one of the ammonias contained in that triangle. Same thing, like I can't draw like one straight line and have it all be chlorines over here. Chlorine, chlorine, ammonia. So this is a different isomer. This is the facial isomer, that's the Meridian isomer. These particular isomers are possible in an octahedral geometry. Now, cis and trans isomers are also possible when we have a carbon with another double bond, so there's no rotation about the carbon bond, but you can also have cis and trans isomers in inorganic complexes. This is possible. Cis and trans are also possible when we have square planar complexes, such as when we have a platinum complex. Now, this is square planar, so it's just one plane, and you can have a complex that looks like this, where they're on the same side, and you can also have the platinum with the trans. I'm just going to draw this one kind of looking down at the top of the molecule. And I'm leaving off all the hydrogens, but you get the idea, they're on opposite sides of the molecule. And this would be trans. Cis configuration, trans configuration in square planar. Tetrahedral geometry does not have a cis or trans configuration, but octahedral and square planar do. And then octahedral further has the facial and meridian isomers. Now, it is also possible for us to have even more isomers than this in an octahedral geometry. If, for example, instead of having all or largely similar ligands around a central metal, what if we had 6 different ligands around this metal? Well, then there's actually 15 isomers for that. And I've never actually sat down and drawn out all 15. But that's not even the end of the story, because there's also 15 enantiomers of those, or a mirror image of each one of those isomers. So there's actually 30 different isomers of a complex that has one central atom and then 6 different ligands around it. And I'm not sure exactly how you would name all of those complexes, but I have a feeling it would get complicated. But I mentioned that just so we could appreciate how many isomers are possible with inorganic complexes. So pay attention to these cis and trans and facial and meridian isomers.